All right, let's talk quickly about the types of matrices we have. So I'll be sharing about 10 different types of matrix or thereabout in this video, and it's very vital to understand the differences between every one of these types of matrices. Now, the first we'll be talking about is the row matrix. Basically, the row matrix is the type of matrix where we have just one row just one row. We don't have more than one row when we're dealing with uh, a row matrix. Under row matrix, it's always having the order. The order of the matrix is always 1 by n. If you remember in my previous video, you would remember I talked about the order of a matrix being written as the number of row, then the number of column. So in a row matrix, we only have, and always we have, just one row. Now we can have multiple columns, and that's why we defined the number of columns as n, meaning we can have different numbers here. Right now in this matrix A, now we can see that this matrix A has an order of 1 by 3. This is a 1 by 3 matrix, one row, 3 different columns. So that's how you identify a row matrix. It's a matrix where you just have a single row and you can have several number of columns. Now, let's go briefly to the column matrix. In a column matrix, we have a similar matrix to row matrix, but in this case, we'll be having just one column. So under the column matrix, we can only have one column, but we can have several number of rows. And that's why we have the column matrix order given as the general form of a column matrix is always given as a n by 1 matrix rather. So in this case now you can see for this matrix A we have a 2 by 1 matrix, meaning we have 2 rows but we have just one column. So when you're dealing with a column matrix, you need to be informed that you cannot have more than one column. So, but you can have several rows. So we can go on to have a 3 by 1 matrix. A 3 by 1 matrix will be a column matrix. A 4 by 1 matrix will be a column matrix. A 5 by 1 matrix will be a column matrix. As long as it doesn't have more than one column, it's still a column matrix. Let's go to the next matrix, a diagonal matrix. Now, diagonal matrix, the peculiarity of this matrix is that every other element, apart from the leading diagonal. Now, let me quickly talk about the leading diagonal. When you're dealing with a square matrix, you need to know that the diagonal that stems from the top left to the bottom right, this is the leading diagonal. So what we have right here is what we call the leading diagonal. Never forget that. That's always regarded as the leading diagonal. And the peculiarity of a diagonal matrix is that every other element apart from the leading diagonal is always zeros. So only the leading diagonal has a non-zero element. So in this case now, there's a way we write the diagonal matrix. So it's possible you define a diagonal matrix by just writing it as diag, and then you write. So you see right here, we have been able to rewrite our matrix A as diag 145. So when you see something given as diag 145, you need to remember that this is indicative of the fact that this is a diagonal matrix, and you should be able to write the matrix out. That means this 145 is always going to be the leading diagonal, and every other element apart from that leading diagonal, which has been stated, will be 0. Now, let's go on to talk about the upper triangular matrix. The upper triangular matrix is of a very distinctive quality in the sense that you can see that how you recognize a upper triangular matrix is that now I talked about the leading diagonal already being the diagonal that stems from the top left to the bottom right. So you can see the leading diagonal as 1, 2, 8 written down there. Now, an upper triangular matrix often have elements below the leading diagonal as 0. So it's more like, you can see this forms the shape of a triangle. You can look at it this way. It forms the shape of a triangle. You can see that this forms the shape of a triangle, but below this triangle, it's an upper triangular. So elements in this upper triangle are non-zeros, but every element below this triangle are zeros. So below the leading diagonal, you have zeros as the element. Above the leading diagonal, you have non-zeros. So you can see, conversely, a lower triangular matrix is similar, with just the difference being that its own is that the lower triangular one, the lower triangle, those in the lower triangle are non-zeros, and in the upper triangle are all zeros. So this is a lower triangular matrix, while this is an upper triangular matrix. All right, let's talk about the square matrix. The square matrix is a unique type of matrix in which we have a matrix having the same number of rows and columns. Now, as you can see right here, these are two examples given. And if you notice from what you have in matrix A, you can see that the number of rows equals to the number of columns. So the order of our matrix will often be having the same number of rows and the same number of columns. So in this case now, the order of this matrix A will be a 2 by 2 matrix. This is the order, because obviously you can see that this matrix has 2 rows and 2 columns. While that of matrix B, we can see that it has 3 rows, row 1, row 2, row 3, and 3 columns. So the order of this matrix will be a 3 by 3 matrix. Now let me quickly share this. Sometimes some people you can see places where, rather than writing a 3 by 3, you will just see someone expressing this as a matrix of order 3. So when you see this, when you hear the word the matrix has order 3, that's telling you that the matrix is a 3 by 3 matrix. On the other hand, you can call this a matrix of order 2. That means it's a matrix that has a 2 by 2 order. A matrix of order 2 means it's 2 by 2. A matrix of order 4 means it's a 4 by 4 matrix. All right, the next thing I want to quickly talk about here is what we define as the trace of a matrix. Now, I already talked about what we call the leading diagonal of a matrix already. In matrix A now, we can see this is the leading diagonal. It is the diagonal that stems from the top left to the bottom right. So this is the leading diagonal 3, 6. While that of matrix B, you can see this is the leading diagonal there. Now, there is something we call the trace of a matrix. When you are asked to find the trace of a matrix, it is always the sum of all the elements of the leading diagonal. So the trace of matrix A now will obviously be given as 3 plus 6. So if you're going to find the trace of matrix A, the trace of matrix A, which sometimes we write it like this, the trace of matrix A is equals to, this matrix A is equals to 3 plus 6. That means the trace is given as 9. Whereas the trace of matrix B, which is obviously also going to be the sum of the leading diagonal. So the trace of B will be 3 plus 0 plus 5, and that will be 8. So that's how you find the trace of a matrix. All right, let's talk about symmetricity of a matrix. A matrix is said to be symmetric if it is equal to its transpose. Now, if you can see the argument that is placed right in front of you, a symmetric matrix is what you call what happens whenever you have this condition being fulfilled. We have a matrix A. Now, if you transpose matrix A, and matrix A transpose is still giving you matrix A. That means after transposing the matrix, which obviously transposing a matrix means you are interchanging the rows and the columns of that matrix. So if you interchange the rows and columns of matrix A, and your final answer is still giving you the same matrix A, then that matrix A is said to be symmetric. So let's try this example we have right here. Matrix A is given as what you have there. Let's go on to find the transpose of matrix A. So we want to change the rows to become the column. So we would be putting 1, 2, 3. This was row 1 as 1, 2, 3. Now we interchange row 1 to become column 1. We interchange row 2, 270 to become column. Row 2 becomes column 2. And row 3, 305 becomes column 3. Now we see what we have right here. Now let's look carefully. Does matrix A equal matrix A transpose? If you can see right here, we say a matrix is equal to each other if every element in this matrix is equal to the other elements in the other matrix. So respectively, all the elements here, that means we check row 1 column 1 is 0, row 1 column 1 here, row 1 column 2 is 0, row 1 column 2 here, row 1 column 3 is 0, row 1 column 3 here. Now if you check through on everything and you identify that these matrices are purely the same thing, then you can say the two matrices are equal. Now if you can observe what you have right here, you can see that A here, matrix A here is equals to A transpose. Therefore, we conclude that A is symmetric. So this is the condition that must be fulfilled for you to say a matrix is symmetric, is if A equals to A transpose. So what does it mean for a matrix to be called skew-symmetric? Let's get into skew-symmetric matrix. Well, the condition to be fulfilled for you to identify a matrix as being skew-symmetric is that A now, don't forget we talked about symmetric being that if A equals to A transpose. But if a situation arises where A is not equals to A transpose, but rather A is equals to negative A transpose, that means it's not exactly A transpose, but if you multiply A transpose by minus, you would be getting your A back. That means your A is the same thing as when you multiplied your A transpose by negative by minus. If that happens, then you would say that A is skew-symmetric. Let's just get into an example very quickly. Look at this matrix A. Let's go on to finding the transpose of this matrix A. If you find the transpose of this matrix A, you will be having, obviously, interchanging the rows to the column. So row 1 becomes column 1. We have 0, 7 minus 5. We have minus 7, 0, 0. We have 5, 0, 0. Now, if you look at this, this is not exactly A. So obviously, A is not equals to A transpose. So that means you can't call this matrix A symmetric. But let's go on to find out if we decide to, if we're deciding to multiply A transpose by minus, that means if we go on to try and find minus A transpose, what are we going to get? Let's go on and do this. Minus A transpose will be us multiplying every element in matrix A transpose by minus. So 0 times minus, we have 0. Then we have minus times minus 7, we have 7. Minus times 5, we have minus 5. Minus times 7, we have minus 7. Minus times 0, 0. Minus times 0, 0. Minus times minus 5, we have 5. Minus times 0, 0, 0. So looking at this, we're done getting minus A transpose. So what then do you notice? If you go on to check this out, you would see that A here equals to minus A transpose. You can see 0, 0, 7, 7, minus 5, minus 5, minus 7, minus 7, 0, 0, 0, then 5, 5. You can see here that we can conclude that A here is equals to minus A transpose. And this is the condition to be fulfilled for us to define a matrix as being skew-symmetric. So therefore, we can conclude that matrix A is skew-symmetric. All right, let's talk about singularity and non-singularity of a matrix. We call a matrix being singular if its determinant is 0. So when you have a square matrix and you decide to get its determinant, if the response from doing that is 0, that means you're going to define that matrix as being a singular matrix. And if you don't get 0, that means if it's not 0, then it's non-singular. And that's why you will see questions that comes in the form of a non-singular matrix. When you hear the word a non-singular matrix, that's basically telling you that the determinant of this matrix is not 0. But if they tell you that a matrix is singular, all they are telling you is that its determinant was 0. All right, let's quickly try and find, let's determine if these matrices are singular or non-singular. All right, matrix A, I told you already that the condition is for you to check out the determinant. If the determinant is 0, it's singular. If the determinant is not 0, anything apart from 0, it's non-singular. So trying to find the determinant of this, obviously this will be multiplication of this minus multiplication of this. So we have the determinant of this being 2 times 4 minus 8 times 1. This will be 8 minus 8. This is 0. Therefore, we conclude that matrix A is singular. This is a singular matrix. A is singular. Let's try matrix B. Under matrix B, we have the determinant of B being given as, of course, multiplication of this minus the multiplication of this. That will be 3 times 6 minus 9 times 2. That would be 18 minus 18. This is also 0. So we can conclude that matrix B is singular. Let's check out matrix C. Of course, you are multiplying the leading diagonal, subtracting it from this diagonal. So the determinant of matrix C will be 1 times 2, that's 2 minus 6 times 3, 18. So what you have here is 2 minus 18, which is what? Minus 16. This is not 0. So therefore, we conclude that matrix C is non-singular. All right, let's talk about the identity matrix, often sometimes called the unit matrix. Well, this is a very special type of matrix which it has the element of the leading diagonal as 1. All the elements of the leading diagonal is often always 1, and every other element as 0. So what you can see right here, you can see this is an identity matrix of order 2. This is an identity matrix of order 3. Now, you can see the uniqueness of this matrix is that it's unitary. It has 1 and zeros as the only two elements you will find in it. And the ones are often always going to be at the leading diagonal. Now, it has a special characteristics that you need to always remember. When you multiply an identity matrix with a matrix A, you always get the matrix back. So if you multiply this identity matrix now with a different 2 by 2 matrix, which is not an identity matrix, you would get matrix A back. So this is what I mean. If you go on to do high times, let's imagine you have an identity matrix multiplied with another matrix. What you will get will always be this matrix back. So an identity matrix multiplied by another matrix will give you the matrix back. That's what you can see right here. So identity matrix times matrix A is always going to be matrix A times identity matrix. Now I need to inform you that matrix multiplication is not always commutative. So I times A is not always A times I if this is not an identity matrix. So A times B is not B times A in matrix. But when you're dealing with an identity matrix, I times A will always be A times I, and the resultant will always be matrix A. Now, another quality of identity matrix is that when you square or raise to the power of 3 or any power of an identity matrix, it's always going to be the same answer. That means this right here is the same thing as if you squared I, the same thing as if you cubed I to any power. It's always going to give you, as long as k right here is a positive integer. All right, let's quickly talk about a scalar matrix. So a scalar matrix is a unique form of matrix also, in which we have every element apart from that of the leading diagonal equals to 0, while that of the leading diagonal is equal to a constant value. So all the elements of the diagonal, the leading diagonal, are equal to a constant value, which we are going to call a scalar. And every other element is going to be 0. So you can see our matrix A now. Every element in the leading diagonal is 5. That means the scalar right here is 5. So this is a scalar matrix where we have the element 5 as the element in the leading diagonal. And the formula we use to often get a scalar matrix is that we have a constant, which is what we call the scalar, multiplied by an identity matrix. That's what will be the resultant of a scalar matrix. For instance, let's take, we have a scalar k multiplied by an identity matrix, a 3 by 3 identity matrix. This is the resultant. So this is a scalar matrix right here. So any matrix you see in which the members of the leading diagonal is a constant value, it could be 5, it could be k, it could be any value, it could be y, it could be x, it could be 10, it could be 7. It's equal to a constant value, and every other element apart from those in the leading diagonal is equal to 0. We call that a scalar matrix. All right, so to cap it all up, let's talk about a zero matrix. So what you have is a zero matrix we can see right in front of us. It's a special type of matrix where we have all the element entries of a matrix being 0. So whatever dimension the matrix has, as long as every element in that matrix is 0, we can call that matrix a zero matrix. And we often write it in this form, where we have 0 then we write the order. 0, then we write the order. So this is a zero matrix. This is a zero matrix. This is what we define a zero matrix as. All right, guys, I really hope you've been able to gain so much from this video, and I hope this has enlightened you on the several types of matrix we have out there. If you have any question, you can drop in the comment section below. I'll be glad to answer. Thank you guys for joining. I hope to see you in the next video. Bye-bye.